Right. So from here, right, that is our function of the slope. Okay. So I'm going to quickly do, right. So this is using all integration. Okay. You have the slope, everything, and so on and so on. So the next one, so sometimes some of these problems, you can also apply the positive shear and the positive bending moment. Okay. Again, I will say again, you can also apply the positive shear and positive bending moment. Okay, so the next I'm going to show on the other side. Okay, side by side. I want you to see for yourself, compare. Okay, I'm going to divide my page until here. I don't think I need the whole thing. Right, so we're going to use positive shear, and I want you to see the difference in the steps. Okay, the most important thing. So for this case, it's pretty straightforward. Just go. You need to know the boundary condition, right? You need to know all this boundary condition over here. All right, you need to know all this boundary condition. Then all you need is to form the equation of the distributed curve and distributed load, and then you integrate. Okay, now if you were to use the positive shear, okay, you were to apply the positive shear and positive bending moment, you can. It's not that you can't. Okay, so let me. Okay, you're going to apply positive shear. So for this case, the first thing you have to do is you have to find the reaction force at point A. You need to find the reaction force at point A first. Okay. So for this case, because the load is very simple, okay, you can use this technique, but you have to be careful on your approach. So this is the load. Okay. So this is your AY. Over here is your BY. And your load over here is omega naught L divided by 2. So this is your equivalent load. Okay, this is your equivalent load. So the equivalent load, we use half base times height, right? Or there's another way to find the equivalent load. Okay, so another way to find the equivalent load is like what we said before. You again have to find, okay, find the equation of the distributed load. I rather you guys use to find the equation of the distributed load. Okay, so when that's the case, omega as a function of x, the slope is omega naught. Okay, so the height is, the rise is omega naught. The x-axis is Lx. Okay, and then the equivalent load function will be equal to omega naught x squared divided by 2L, right? And if we put our limits, okay, if we put our limits from 0 to x, right? So this is a function of x now. So what we have is equal to omega naught x squared over 2L. Okay. Now, why we did not get L over 2 over here? Why this is not the equivalent load? We have it as a function of x. So if we're going to find the equivalent load, okay, we can find the equivalent load, okay, for the entire length. Right? So this will be equal to, you go from 0 up to L omega naught x squared over what? 2L? Yes or no? Hey, what am I doing? This is omega naught. Yes, I do apologize. Omega naught x over L. Okay, so omega naught x squared. Yep. So this will be equal to omega naught writing too fast. Right? So this will be equal to omega naught x squared over what? 2L. And then if you put in your limits 0 to L, you have this is equal to omega naught L squared over 2L. So it's also equal to omega naught L divided by 2. Same. Okay. So you find the reaction force. Okay. So now we have to find our reaction force. And we know the distance from here to here is L over 3. Okay, so we're going to take moment. We're going to take moment. So I mentioned about moment, Z, and we're going to take at point 2B, the whole thing is equal to 0. Right? So we know that is going anti-clockwise, omega naught L divided by 2 multiplied by L over 3. Right? So that is going clockwise at point B. And then the AY is going anti-clockwise. Sorry, it's going clockwise. AYL, the whole thing is equal to 0. Right? So you have omega naught x squared over 6 minus by AYL, the whole thing will be equal to 0. So we found that AY is equal to omega naught L divided by 6. Okay? Then you use positive shear and positive bending moment. So you write from point A to point B, right? 0x to L. Okay. So you have over here. So this is your point A. That's why you need it to find AY. You don't need to do BY. Okay. So this is equal to omega naught L over 6. This is a function of x. V as a function of x. M as a function of x. So we have a load over here, and the distance from here to here, we know is what? X over 3. Now, what is this equivalent load over here? Okay. So this is now the equivalent load is this expression over here. Omega naught x squared over 2L. Okay. Computer not behaving again. Sorry. Yeah, today this is a crappy computer. Hold on, people. Can you still hear me? Yes?
Yeah, we could hear it. Just your screen is frozen.
Yeah, stupid screen. Wait, let me yeah. Okay. I'm going to reboot my computer again. Okay, I'll be back. Okay, I'll be back about Can you hear me now?
Yes, we could hear.
Okay, good. I'm back again. But I have not a clue I'm not a clue whether is the screen back. Yeah. Well, okay, right?
Screen's back.
Okay. So now is this equivalent load down here, right? So it just looked weird all of a sudden, right? So now we want to find what is this equivalent load, right? We want to find what is this equivalent load over here. So that's where it's good, right? That's where it's good. Gee, what happened here? Yep. Let me tidy things up down here now. Okay, so what's happening down here now? So that's why it's important to write out the equivalent load equation. Okay, it's equal to omega naught x squared over 2L. So when you have this as a function of x, right? When you have it as a function of x, this is equal.
If you scroll up, the wording is kind of messed up. It's like scribbled over.
Yeah, I can see that now. Thank you for telling me. Okay, I will rewrite AY L. This is equal to omega naught L squared over 6. Okay, I think that's the only place. Right? Thank you for catching that. Okay, I did not see that. Right. So now you can see, right? So this, you have to use this expression over here. You cannot use the expression where it's what? Omega naught. You cannot use omega naught L over 2. Because omega naught L over 2 is for the what? Entire length. Okay, so we substitute for the entire length. We substitute for the entire length over here. Right, we substitute for the entire length over from 0 to L. That's why you have omega naught L over 2. But if you substitute as a function of x, your equivalent load is omega naught x squared over 2L. So something to be mindful, something to watch, because I made that mistake before. Okay, so from here, we know that this is equal to omega naught x squared. Right, omega naught x squared over 2L. Okay, so once you got this right, so we also know the distance from here to here. This is x over 3. So that's where we have positive is going up again. So this is the easy part. Once you got that done, it's equal to 0. So this will be equal to omega naught L over 6, right? And then you have minus omega naught x squared over 2L, right? Minus v as a function of x is equal to 0. So you have v as a function of x will be equal to minus omega naught x squared over 2L, right? Plus by omega naught L over 6. Okay, so this is your Vx. So if we look at our expression, if we look at our integration method before, again, I am so pissed off with the computer now. Now everything is gibberish. Okay, it's okay. So if we were to look over here now, okay, I'm going to quickly correct this. Okay, so if we were to look this expression over here, I do apologize for this. Okay, so this will be equal to v as a function of x. So this is equal to minus omega naught x squared over 2L plus by C1, and this is equal to dm by dx. Okay, so if you look at equation number 1 down here and compare that what we have just got, right? So we have omega naught x squared over 2L. We have omega naught x squared over 2L. Down here we have it as C1. Down here we know the exact value is omega naught L over 6. So if you look at C1 over here, later on we found it's also equal to what? Can you all see what I've just circled? Yes or no? Right? Can you see what I've circled? So we have
Yes.
what I've, okay, thank you. Thank you. It's the computer, okay? We have omega naught L. So it's the same, yes or no? So what I'm trying to say down here, if you use this technique, you don't need to use boundary condition in terms of you don't need this boundary condition at all, right? You don't know and you don't need it, right? Then the next one, you will use your you will You will find your moment now.